Alright, welcome back. In this, we're going to go over Oxymercuration-Demercuration. I made a lifetime total of $320.90. Alright, Oxymercuration-Demercuration is the second type of hydration reaction we'll go over for alkenes. This is actually one of my favorite reactions to go over. It's actually really interesting. When doing acid-catalyzed hydration, which was the last mechanism we went over, it's the first hydration reaction we learned, there is a chance that your reactant will undergo carbocation rearrangement, right? Because when we did acid-catalyzed hydration, this reaction you see here, the double bond, the pi bond, would attack hydronium. And what would happen is the hydrogen went to the less substituted carbon, and the carbocation would go to the more substituted carbon, like this. Now, if the carbocation has the ability to move to an adjacent carbon where it is more stable, it will do so via hydride shift or methyl shift. Now, here is the very easy way to determine if you're going to do a carbocation rearrangement. This is like the cheat sheet. First, look at your carbocation. Then what you're going to do is look at the adjacent carbons. Only adjacent, only next to each other. Only the carbons next to the carbocation. If it is more substituted, that's the first check. Okay, if it is more substituted. So let's take a look here. This is where our carbon is for the carbocation. The adjacent carbons is this one and this one. This one is more substituted than this. So that is a potential carbon for carbocation rearrangement. You can move the carbocation there. The next step is to see, first, is there an available hydrogen? If there's not an available hydrogen, then look, is there an available methyl group? Well, we can see that this carbon does have an available hydrogen, because this carbon only has 3 bonds shown. But in reality, carbons must have 4 bonds, so there's an invisible hydrogen. So what we can do is move that hydrogen and have it attack the carbocation. So basically, you just move it over. And when you do this, the hydrogen will now move here where the carbocation was. And now the carbocation will go to the carbon. And now it is more stable. And then you would do the rest of the reaction. Do you know what we call this? We call this a big waste of time. Look, come on, chemists are lazy. Do you really want to do all of this? Right, when you do acid-catalyzed hydration, like on a test, you do the reaction, and like, oh my god, then you have to do carbocation rearrangements. It's a whole nother step. That's another like 5 minutes that you have to think about. Do you really want to do that? No. So that's why chemists came up with Oxymercuration-Demercuration. What this mechanism does, it avoids the carbocation rearrangement step by adding mercury and some other stuff. Okay, here is the overall reaction. Here's what we're doing. We have our alkene. So the whole goal of Oxymercuration-Demercuration it's a hydration reaction. So we're adding water across the double bond, which, well, it's no longer going to be a double bond, but we're putting an OH and a hydrogen, which ends up as H2O, right? Because that's 2 hydrogens and 1 oxygen. So we're technically adding an OH and water on the molecule, but, it's water. Okay. So we have an alkene. The first step is called oxymercuration. Here's what we're going to be doing. We're going to be adding a molecule called mercuric acetate, which is this. That's all it does. The OH that you see here that has been added is from the nucleophile. It is not from mercuric acetate. Mercuric acetate only helps to add the nucleophile. That's it. So these are 2 separate things that are happening. And the oxymercuration is just this step. The nucleophilic attack adds the alcohol. Okay. Now we have this. Now we have to do something called demercuration. In other words, get rid of the mercury, the mercuric acetate molecule. So we are left with just our OH and then the water that's actually there, that's hidden. So here's the recipe. What we need to do this reaction. We have our alkene. The first thing we need is mercuric acetate. It's HgOAC2. Followed by the comma is the nucleophile. This is what we're going to be adding to our molecule. This will add the OH group. Now you'll notice that you see a number 1 here and a number 2 here. This may be the first time you're going to be seeing this. But what this means is this stuff belongs in the first step of the reaction and this belongs in the second step. That's all it means. You treat it as different steps. So after we add the OH group, the alcohol, we have to do demercuration. And we're going to use sodium borohydride. And what this does is it adds the hydrogen. Because remember, hydration reactions will add H2O in the form of alcohol and hydrogen. Well, this is going to be doing this, and this is going to be doing this, right? Adding the OH. Now, here's a bonus thing. Oxymercuration-Demercuration is not only for hydration reactions. We can actually use these two reagents to do other types of reactions if you want to add other molecules to our compound. We don't just have to use water as a nucleophile. We can use other things. I'm going to show you an example later on in the challenge problem. Okay, here's the mechanism. Before we actually do the mechanism, we have a prep step. Like I said, we have mercuric acetate, right? This is this. Well, mercuric acetate actually just breaks apart into mercuric cation. This is our electrophile. So this one acetate breaks apart and it goes bye-bye. We don't care about it. It leaves. We are left with this mercuric cation. It has a positive charge, which, positive charges are great electrophiles. It's fantastic. This stuff is this. That's what acetate is. This is acetate. This is acetate. This is the same thing as this. It's just written differently, drawn differently. It's the same thing. This is the same thing as this, and this is the same thing as this. They're all the same. I just drew it differently, so you know what it looks like. Okay. Now I said our nucleophile is the water, but that's later down the road. But how do we kickstart the reaction? Well, when you have an alkene, the first thing you need to do is the pi bond attacks your electrophile. So your pi bond from the alkene is going to be the first nucleophile, and it's going to attack our electrophile, which is our mercuric cation. Okay, let's do the actual mechanism. Here's what's going to happen. We're going to take it slow. The pi bond is going to attack the mercury atom. Now here's what's going to happen. This may look a little complicated. What's going to happen is the mercury or mercuric acetate compound here is going to bind to the less substituted carbon. So you'll notice that this is the more substituted carbon, this is the less substituted carbon. This is going to bind to the less substituted carbon. Now, here's the thing. The mercury atom has a lone pair. And it's going to attack what we see is the carbocation. And it's going to create this 3-membered ring structure. This 3-membered ring. Now, what's really happening is all of this happens immediately, super fast. We can legally not call this a carbocation because the mercury, which is already attached to the molecule, is attaching to the molecule itself, causing a ring to form. Whenever you have an atom that is part of your molecule and it attacks a different part of the same molecule, you're like this, right? So it's already attached to your molecule, and it's attacking another part of the molecule to attach and form a ring. We cannot call this a carbocation. Just legally, we're not allowed to call it. This is a ring-forming reaction. So, in other words, what's really actually happening is when this pi bond attacks to mercury, mercury wants to hold on to both carbons at the same time. That's what's really happening. And how it happens, how it actually holds on to both carbons, is because the electrons attack here. That's how it's holding on, and that's how it's creating this ring-like structure. So, once again, what's happening is the mercury atom is attaching to the more substituted carbon and the less substituted carbon of where the alkene was, where the pi bond was. Okay. Now, to compensate for this positive charge, right? This positive charge that was there, now we form this ring. There is a partial positive charge between the more substituted carbon and the mercury atom. Like this. There's a partial positive charge and a partial positive charge on the mercury. This is due to resonance. This is our resonance structure. Okay. Since we have a partial positive charge, this will get attacked by our nucleophile. Because remember, nucleophiles like positive charges or partially positive charges. So water is going to come along, because remember I said water's our nucleophile. So now it's now water's turn. Water's going to come in and attack our partially positive carbon on the more substituted side. This is going to cause like our normal acid-catalyzed reaction like we've been doing. So that's what's going to happen. Water's going to add here. Now notice that oxygen has a positive charge. Oxygen cannot have a positive charge. That's part of water. So we're going to use more water to deprotonate it. Get rid of this proton to help stabilize this charge, right? So it's going to break apart and then stabilize that. I should actually draw that in red. Okay, there we go. So now we have our OH group here. We're halfway done. So the OH is now on the more substituted carbon. We're still left with this crap there. So we had to get rid of it. We're going to use sodium borohydride. Now, what really happens, the mechanism for this is a whole nother thing. It is so complicated with multiple steps, radicals involved. Don't worry about it. You'll never be tested in basic organic chemistry, or Ochem 1. You will never be tested on how to do this mechanism because it's just so overly complicated and long. We don't have time for that. But what you need to know is sodium borohydride will give off one of its protons in exchange for getting rid of this. So it replaces this with one of the protons on sodium borohydride. So it becomes NaBH3. That's what happens. And now we are left with our final molecule here. OH on the more substituted carbon and hydrogen on the less substituted carbon, which is water. There we go. And that is the mechanism. So it's not too bad. The hardest part is just remembering this part. And it's honestly, it's kind of easy. Like this atom always goes to the less substituted carbon, and then the mercury attacks the positive charge on the more substituted carbon, creating this ring. And then you just do your water reaction, just like acid catalyzed hydration on the more substituted carbon. Okay, Let's do some practice problems. Predict the product of oxymercuration reaction. In addition, tell me the product of the reaction if it were to undergo acid-catalyzed hydration. Okay, this is how you do it. So easy. It's so easy. We're adding OH and H, right? OH goes on the more substituted carbon than Markovnikov product. So I'm going to copy this. Copy. Like that. Okay. Here's our alkene. This is the less substituted side. This is the more substituted side. So the OH is going to go here, and the hydrogen is going to go here. It's that easy, right? So that's the oxymercuration-demercuration answer. OH and our hydrogen. Actually, you don't even need to draw in the hydrogen. I'm just drawing it in, but that's how you would actually draw it in. That's the answer for oxymercuration reaction. It's that easy. Okay. What about acid-catalyzed hydration? Okay. Well, if we were to get rid of this double bond there, right? We get a positive charge, a carbocation there. You'll notice that if you look at the adjacent carbons, this is more substituted than this. So we can move the carbocation there if we have an available hydrogen or an available methyl group. Well, this carbon has 1, 2, 3, 4 bonds. That means there's no available hydrogens. So now we have to look for methyl groups. We indeed do have a free methyl group, so we can do that. So what we can do is just move this here, and the carbocation will go here. So let me just copy that. Okay, so we are adding our methyl group. Actually, let me make this more proper. Like that, that's more proper. So that is now our methyl group there. The carbocation is now there now. And then since the OH group, an acid-catalyzed hydration, attacks the more substituted carbon, which is the carbocation, the OH group will go here. Like that. And that's the answer for acid-catalyzed hydration. Okay, let's do the bottom one. This carbon is more substituted than this one. So the OH group is going to go here, and the hydrogen is going to go here. That's how fast. See how fast it is? So, let me draw that in. And then the hydrogen would be here. So that's the answer for oxymercuration-demercuration. What about acid-catalyzed? Okay, well, if we remove this double bond, the pi bond there, we have a carbocation here. If you look at the adjacent carbons, this is more substituted than our carbocation we currently have. So we can move the carbocation if we have a free hydrogen or a free methyl group. This carbon has 1, 2, 3, 4 bonds. It does not have an available hydrogen, but it does have an available methyl group. It has actually 2 of them. We can use either one of them. So what we're going to do is have this attack the carbocation to move it over. And now the carbocation is going to move to here. Come on. There you go. Okay, so this goes away, go this way, this goes away, this goes away. Actually, let me redraw that. Like I said, the methyl group now goes here, like that. We are left with a carbocation here, where we transferred it to this carbon. And I said that the OH group goes to where the carbocation ion is, or the more substituted carbon. Like that. And get rid of this. And that is our answer for acid-catalyzed hydration. So you can see the differences between oxymercuration and the acid-catalyzed. And oxymercuration-demercuration is easier. It's so much easier, right? You can just look at it. No, you don't have to worry about anything. Just look at where the alkene is, figure out which one's more substituted, and put the OH there. And put the hydrogen on the other side. It's that easy. All right, challenge. What happens if your nucleophile isn't water? We are no longer doing a hydration reaction. Tell me the product. Okay, we have this. What the hell do we do? It is the exact same thing, except you put this instead of the OH, but you remove one hydrogen. That is the trick. So it's like just adding the OH group like normal, but you remove one hydrogen. That's the trick. So let's just think about it logically. When we did our reaction for oxymercuration-demercuration, we have H2O, 2 protons and 1 oxygen. But when we add it to the molecule, you're only adding 1 oxygen from the H2O, 1 oxygen, and 1 hydrogen, which becomes OH. The other hydrogen is coming from sodium borohydride. Okay, so the nucleophile is only providing 1 oxygen and 1 proton. The other proton's coming from sodium borohydride. So whenever you add anything from the nucleophile, so whenever you give it a nucleophile and you're supposed to add it to the molecule via oxymercuration-demercuration, what you're adding is everything shown here minus 1 hydrogen. That is the cheat code. So that's exactly what we're going to do. Take this, copy it. All right, this is the more substituted carbon. This is less substituted carbon. So this nucleophile is going to attack this area right there. So delete that. Okay, what do you have? You have this, and you have a nitrogen. You have an ethyl group. And then we have our hydrogen. Even though it says 2 hydrogens, we subtract 1. Whenever you have the nucleophile, always subtract 1 hydrogen and add it to your molecule on the more substituted side. That's the answer. This is it. See how easy it is? That's the cheat code. If you were given, okay, let's do this one. If you were given ethanol instead, let's just do ethanol. If I was given ethanol, okay, erase this. It's gonna be oxygen with our ethyl group. That's it. No hydrogen. You don't include it, and that's our answer. So see, that's a cheat code. It's pretty easy. And that's it. If you found this video helpful, please like and subscribe. Until next time, later.